Hi everybody! So in today's video we're going to dive a little bit deeper with the idea of implicit differentiation, and we're going to look at some of the ways that we can use implicit differentiation to answer other questions about the slope of a function. So the first big idea today is that we are going to be finding where the slope of a function is undefined. In order to think about where a slope is undefined, we need to remember some interesting things about slopes. So if you're looking at a graph, a slope will be undefined when there is a corner, a cusp, a vertical tangent line, or a discontinuity. When you're looking at an equation, a slope will be undefined at an x value that makes the derivative undefined. Another big idea that we're going to be thinking about is the idea of where a function has a horizontal tangent line. So it's important to remember some interesting things about horizontal tangent lines. If you're thinking about a graph of a function, the tangent line will be horizontal. So let's pretend this is our function. The tangent line will be horizontal at the top and the bottom of a mountain or a valley, because that's the place where the tangent line would be horizontal. It would be flat. From an equation, a tangent line is going to be horizontal at an x value that makes the derivative equal to 0, because the slope of a horizontal line is 0. So using those two ideas, we're going to answer the question for problem 1. It says here, the derivative of the curve x squared plus xy plus y squared equals 7 is dy over dx equals negative 2x minus y all over x plus 2y. So in this problem, you've already been given the original function and the derivative. For part 1, it says find all the points where the slope of the curve is undefined. Now, we need to make sure we really understand this question. The first thing is, it asks me to find the points where the slope of the curve is undefined. We need to remember that a point always has an x coordinate and a y coordinate. The second thing we really need to be able to pick out of these instructions is that the slope of the curve should be undefined. Undefined means that the derivative does not exist. So if we go to our derivative equation here, we're going to want to find the place where dy over dx, which is equal to negative 2x minus y, over x plus 2y, does not exist. In order for a fraction to be undefined, we're going to take the denominator and we're going to make it equal to 0, because being equal to 0 in the denominator would make our fraction undefined. Now you'll notice that if we set up an equation that says x plus 2y equals 0, there are two variables in this equation. So just using this equation, it's not possible to find specific values of x or y. However, I do have another equation from the directions that I can use to help facilitate finding x and y. In addition to having the derivative, we have the equation of the original function. So what I'm going to do is a technique called substitution, which you may remember from learning Algebra 1. The first step is to isolate one of these variables. I think it's easier to get x by itself here by just subtracting 2y on both sides. Now I'm going to take this equation and I'm going to replace all of the x's with negative 2y. So in this equation, I'm going to have negative 2y squared plus negative 2y times y plus y squared equals 7. If I simplify this equation, I'm going to have 4y squared minus 2y squared plus y squared equals 7. Now 4 minus 2 is 2, plus 1 is 3y squared equals 7. I would divide by 3, so y squared equals 7/3, and then I would square root, so y equals plus or minus the square root of 7/3. That tells me that there are two locations, 2 points, where the slope of the curve is undefined. However, I need to write these as ordered pairs. So now I'm going to have 2 ordered pairs that I need to figure out. The first ordered pair is going to have a y value of the square root of 7/3. And the second ordered pair is going to have a y value of the negative square root of 7/3. What I'm going to do to find my x is take these y's and plug them into this equation where I found out that x is equal to negative 2 times y. So my x here would be negative 2 square root of 7/3, and my x here would be positive 2 square root of 7/3. And I got that again by just plugging the y into this equation, and that would be my final answer. For part B, it says find the points where the tangent line is horizontal. Again, you'll notice that in the instructions it says the points. So that means I'm going to need an x coordinate and a y coordinate. The other important piece of information here is that we want the tangent line to be horizontal, which tells me the slope should be 0. Because the slope of a horizontal line is 0. So I'm going to take my derivative equation, dy over dx equals negative 2x minus y all over x plus 2y, and I'm going to make that equal to 0. And the reason I'm going to make that equal to 0 is because I want to know where my slope, where my derivative, is equal to 0. Now when I'm solving an equation like this, I find it easiest to use the technique of cross multiplication. So I like to put 0 over 1 and then cross multiply. 1 times negative 2x minus y is just negative 2x minus y, and x plus 2y times 0 is just 0. Once again, you'll notice we have one equation with 2 variables. So I'm going to get one of these variables by itself. I'm just going to add the y to move it to the other side. And then I'm once again going to substitute that into the original function because that's the other equation that I have. This time, however, I'm going to be replacing all of the y's with negative 2x's. So I'm going to have x squared and then plus x times, instead of the y, I'm going to put negative 2x, plus, instead of the y, I'm going to put negative 2x squared equals 7. From here, I'm going to go ahead and simplify, so I'm going to have x squared minus 2x squared plus 4x squared equals 7. I'm going to combine like terms, so 1 minus 2 is negative 1 plus 4 is 3x squared equals 7. I'm going to divide by 3, so x squared equals 7/3, and I'm going to square root both sides, which gives me 2 answers, which is the square root plus or minus of 7/3. Once again, however, I need points, not just an x coordinate, so I'm going to make 2 ordered pairs here. This time, I know the x coordinate should be positive root 7/3 and negative root 7/3. Using that information, I'm just going to plug it into this this equation to get y. So negative 2 times root 7/3 is negative 2 square root of 7/3, And negative 2 times negative root 7/3 is positive 2 times root 7/3. And that should be my final answer. Next, we're going to look at finding the second derivative using implicit differentiation. So in order to find the second derivative, the procedure is always to take the derivative of the first derivative, which is dy over dx, and then we're going to substitute that dy over dx back into the equation to create an equation that only has x and y. So let's look at an example. In order to find the second derivative here, I'm going to need the first derivative to start with. So I'm going to start by using implicit differentiation because the y is not by itself. My first derivative here would be 9x squared minus 6y times dy dx equals 0. Now I'm going to get the dy over dx by itself. So I'm going to have negative 6y times dy over dx equals negative 9x squared. I'm going to divide by negative 6y, which gives me negative 9x squared divided by negative 6y. And I'm going to simplify that because I know that I'm going to be going further. I'm going to be taking the second derivative, so having the simplest form of the first derivative is going to make my life easier. In order to simplify this, I'm going to just reduce these coefficients. So since they're both divisible by negative 3, I'm going to make this into 3x squared over 2y. So that's kind of step 1, find the first derivative. Step 2 is take the derivative again. So the second derivative here, I'm going to have to use quotient rule. So low d high, which is 6x, minus high, which is 3x squared, d low. The derivative of 2y would be 2 dy over dx. And low squared, which is 2y squared, goes down below. What you'll notice is that in the second derivative equation, we have a dy over dx. So my next step is going to be to replace this dy over dx with the equation that we found for dy over dx. So what I'm going to have is, and I'm going to simplify a little bit as I go, 2y times 6x is 12xy minus 3 times 2 is 6x squared, and now I'm replacing the dy over dx with 3x squared over 2y. On the bottom, I'm going to have 2y squared, which is 4y squared. Now it's just a deal with simplifying. So what I notice is that the 6 is divisible by 2. So I'm going to change this 6 to a 3, and I'm going to cancel the 2. And now the only thing that's left in the denominator is y. So I'm going to multiply everything in this equation by y in order to get this y to cancel. So I'm going to distribute the y to the first term here, which gives me 12xy squared. Then I'm going to have distributing the y to the second equation. Since the y cancels this y, I'm just going to have negative 3 times 3, which makes negative 9 x to the fourth, because I have x squared times another x squared, and the y again cancels this y. And on the bottom, when I distribute the y, I'm going to have 4y cubed. And this is your second derivative. All right, last but not least, one very big and important idea in calculus is recognizing implicit differentiation when we're not using x and y variables. So we know we need to use implicit differentiation when the y is not isolated in an equation. But it's also important to recognize when we need to use implicit when other variables besides x and y are used. So for example, a lot of times our derivatives on the AP test look like this. dh over dt equals 3 parentheses 4 minus h. If you read this notation, this h being on the top tells me that h is the output variable, which means it's acting like a y in this equation. And it tells me that t is the input variable, which means it's acting like an x in this equation. I can tell that because our output variables are always on the top and our input variables are always on the bottom, change in y over change in x. What that means is that in problem number 3, where it says, here's your derivative, find the second derivative, I need to recognize that the y, the output, is not isolated in this equation. It's part of the equation. So, if I want to take this derivative, I'm going to need to use implicit differentiation. The first thing I like to do here before I take the derivative is the second derivative is I like to simplify the first derivative, just like I did in the previous problem. For me, this is going to be a lot simpler if I distribute that 3 and I make it 12 minus 3h. Now you'll notice that this is still just dh over dt. I haven't changed to the second derivative yet, I've just rearranged the first one. So my second derivative then would be the derivative of 12 is 0. The derivative of negative 3h would be negative 3 times dh over dt. Now just like in my previous problem, I know dh over dt. I have it right here. So I'm just going to replace that in this equation, just like I replaced the dy over dx in the previous example. So d squared h over dt squared equals negative 3 times, and I'm going to replace that with 12 minus 3h. Now you can leave your answer like this. You could, if you wanted to, distribute the negative 3. It doesn't really matter, but this at the end of the day is your final answer. The catch here is that a lot of students don't realize that they needed to put a dh over dt here because they don't realize that h is kind of like having a y in this equation. So it's really important that you watch for that. Last but not least, actually, you know what, let's stop there for today. We will do the last few examples in class tomorrow, and thank you so much for watching this video. I will see you then.